Good day and welcome to the Digital Transformation webinar series. My name is Stefano Polidori from the ITU. Today's episode number 26 will discuss digital transformation of mobility, paving the way for road safety. The process of digital transformation may influence the future of mobility by leveraging emerging technologies. It is of utmost importance to take road safety into account in this process. Through this webinar, we will explore how technologies such as AI can support different levels of automation in automated driving, while facilitating enhancement of the road infrastructures and enabling more effective post-crash responses. We have an excellent lineup of speakers today, so please stay tuned with us for this webinar. Also, we have a chat box, and I'd like to invite all of you to type in your city and country from where you are connecting from. To kickstart the webinar, I'm honored to pass the floor over to Mr. Seizo Noe, Director of the Telecommunications Standardization Bureau of the ITU, to give us his opening remarks. Over to you.
Friends and colleagues, welcome to this 26th episode of our webinar series on digital transformation. We are achieving remarkable breakthroughs in science and technology. As the UN Specialized Agency for Information and Communication Technologies, ITU aims to ensure that these breakthroughs benefit everyone, everywhere. Advances in AI, automation, digital twins, and connectivity are giving rise to a wealth of opportunities to improve road safety. But new technologies' success in improving road safety will depend on their success in earning public trust. Today's talks will focus on the actions required to build this trust. And I thank all expert speakers for guiding this important conversation. ITU standards for road safety include specifications for vehicle emergency calls and secure over-the-air software updates to connected vehicles. I am also glad to highlight that a new ITU standard is under development to define an automated driving safety data protocol. We are supported by our long-standing partnership with UNECE, the UN agency which provides a global regulatory structure for vehicle and road traffic. Our partnership helps ITU to develop technical standards aligned with the priorities of vehicle regulators. ITU standards are the result of strong will to come together and build consensus on the way forward. Working together on ITU standards, we can reinforce global actions to ensure that new technologies lead to safer, smarter mobility for everyone around the world. Thank you.
Thank you very much, Onoe-san, for those remarks to set the stage for the remaining portion of this webinar and for the discussion that we will have. Before I hand the floor to the moderator, I'd like to remind our audience to use the second Q&A box to type in any question to our panelists, who will do their best to answer. And now, without further delay, I'd like to pass the floor over to Mr. Brin Balcombe, Autonomy Systems and Regulatory Expert at Oxbotica, who has been the chair of our focus group on AI for autonomous and assisted driving over the past 3 years, I'd say. Very recently, the focus group concluded activities and passed them over to the formal standardization process in study group 16 of the ITT. Brin, the floor is all yours for moderating this session. Thank you very much.
Super, thanks, Stefano, and many thanks for the invitation to host this really interesting panel. So good morning, good afternoon, good evening to everyone that's just joined. There's a real mix of different countries of the participants, so that's great to see. Today's session will have 4 speakers, a really good mix of academic and also commercial companies. Each speaker will have around 10 minutes, and then we'll have a short Q&A at the end. As Stefano just mentioned, please use the Q&A box, and the speakers will be able to respond in text in that box. Our first speaker today I'd like to introduce is Paul Lamb from Too Simple. We'll be discussing autonomous trucking, giving you some highlights as to what autonomous vehicles are, and a bit of detail then about how to bring those things to market in terms of policies, standards, and safety requirements. So, Paul, over to you.
Thank you very much, Brain. I'll just share my screen. So, hi everyone. My name is Paul. Before Too Simple, I was working at the Asian Infrastructure Investment Bank as an investment as well as strategy officer, pushing the infratech agenda at the G20. So I had this experience on both sides, the road side as well as the vehicle sides. So today I'm going to talk about safety, and it is everything for the future. That's the foundation of road as well as our transportation. Now, although I've worked in the autonomous vehicle sector, this is not a Silicon Valley thing, although I am in there. And it should be boring because there are so many moving pieces in a complex system of systems with a lot of conflicted interests. Conflict is not bad, but simply it represents the complexity of the road as well as different passengers and vehicles usage. Now, you can imagine that every autonomous vehicle, just like any other internet startup, as well as the tech startup that you have seen, we like to talk about design thinking, agile startup. Now, there are a couple of sectors that these mindsets do not work, just like healthcare, just like agriculture. And autonomous vehicles is also the same, that you cannot use design thinking, you cannot use agile testing if you are playing with lives and criticality. So this is why this means to be a boring presentation, and it should be. And many of the technology startups, as well as people like myself working, there needs to be a lot of respect. So before we talk about safety, I just want to set the scene. And it's so important that we get down to the ground, working on the foundational level of technology and pay a lot of respect to the complexity as well as the weight of the stuff that we're working on. So what is autonomous vehicle? I try to use the SAE and you've all seen this. So from level 0 to level 5, but I try to tend to simplify it. So level 0 basically meant nothing. Level 1 is one-dimensional driving. So either longitudinal, so there's an assisted like lane shifting or something like moving you back into the lane. Sorry, not lane shifting, but staying in the lane, or maybe a cruise control, but only one-dimensional. Now, level 2 is two-dimensional, meaning that I will be able to help you to adjust your position in the lane as well as adjusting your speed. So there are two-dimensional adjustments happening at the same time. Now, level 3 becomes parental control. So basically, you are just cruising and then the car will actually drive itself, but you are still the person who is responsible. Now, L4 is where the real autonomous driving starts, but it is autonomous somewhere, not everywhere. And L5 is omnipresent everywhere. Autonomous driving, that there is no operational domain limitation. So that's a simplified version. Now, how AV works, I think that's really important. Just like a human body, we look at information and then we start planning and then we start controlling the car. Now, I highlighted planning because it is the part that is the least researched, and it is the part that actually is the most hard. Sensors, perception, prediction, I'm sure Brain can talk a lot. There are a lot of open source stuff. There is a lot of collaborations around those things, but planning is where, you know, the magic tricks typically happens and the differentiation starts. Control is also very specific to different cars because you're still having different brands of cars, whether it's electrical vehicle, whether it's commercial vehicle. The control, the trajectory, it's all different. So the planning and control are actually the secret sauce, and every company is slightly different. Now, if we take back autonomous driving, what we are doing at Too Simple is autonomous trucking. Now, today I'm presenting on my personal basis, and I would like to send this message. autonomous driving and autonomous vehicle are two different things. So autonomous driving is really about driving. So if everyone like ourselves have driven a car, typically what we do, driving is only part of what we're doing, right? Sometimes we need to move stuff from our back trunk. Sometimes we need to move the baby. We argue with our second seaters. We might be taking phones, right? Illegally on a hand-free. So autonomous vehicle is a bigger concept. Just like here, autonomous trucking is a bigger concept than just driving, because there needs to be an infrastructure that you need to do fleet management, you need the mapping, you need the connectivity for the remote control. So I just want to get this concept. Autonomous driving is a subset of autonomous vehicle, which can be defined by robotaxi, trucking, and everything else. Now, why does this matter before we go into the safety? Now, we see, for example, road freight is dominating in US. So big trucks, Class 8 vehicles is everywhere, and it is the backbone of our economy. And this is an 800 billion plus market and almost similar in China and 500 billion in Europe. Now, this is really important. Now, if we're talking about inflation, one of the biggest sources of inflation comes from the trucking driver shortage. And the shortage is everywhere. Now, without the drivers, it's harder to get in the truck freight, and then the price goes up. But if we take a step back, thinking about the business challenge that we have, the labor cost, increasing freight rates, increasing fuel cost, what often get missed out is that the labor shortage is also a fundamental issue about health and safety. If you go out and ask the US drivers, why wouldn't you drive a Class 8 trucks? They said, well, if I'm picking this lifestyle, I would have been better off if I'm just driving Uber. So there is an 80,000 to 100,000 truck driver shortage in US only. And this actually is hiding a bigger issue about health and safety, that people don't want to drive so far repetitively, 10 hours on the road without any other stimuli that often make the trips very boring and dull and dangerous. Now, how do we think about safety then? So if autonomous vehicle and autonomous trucking is really the future, today I'm going to focus a little bit more what we as policymakers, as well as the commercial stakeholders, can think about safety. Now, before we think about safety, we need to get back to that claim that I've just said. Autonomous driving is a subset of autonomous vehicle. The real right way to look at this sector is, first, you need to segment it. You need to segment it by a 2x2 matrix. What are you carrying and where are you operating? Now, the 4 grids model, in my view, dictates the way that you think about regulations. Now, sometime you might be thinking, okay, I wouldn't have a blanket-wide autonomous vehicle policy, but let me just give you one example. Here are the 5 key trade-offs that you will be doing. Now, if you are on the easy side in cargo, you can always stop the car. But when you have a passenger, we have all been on a very crazy flight catch. If the car just stops itself in front of the red light, when it's turning red, it's actually okay for you to go. But the algorithm probably would take a more conservative stance. But when that happens, the passenger will actually feel bad. So there is an extra layer of serviceability than actually running a cargo, that you can always do a maneuver in a minimum risk condition with the cargo without anyone actually complaining. So the trade-offs are actually very subtle. And that means the context, the business model, as well as the regulations would be different. This is why when we actually think about safety, we need to first think about what are the different contexts. And one very key message here is driverless doesn't mean there is no one in the vehicle. And that really changes the matrix of regulations and how we think about everything. AV in robotaxi is not the same as no people in the car, whereas in autonomous trucking, often it is the case. So there are a lot of technology that are different. So again, your perception range has to be longer for the trucks and lower for the passenger vehicle, and that all changes the regulation. Now, policy plays a big role. And I will skip this slide because this is very important and it's yet very simple. Now, but the regulations differ. Every state has their own regulation, and this creates regulatory arbitrage. So if we understand that regulation matters, we need to have a regulations for each of the different segment, then the regulations need to harmonize. Yet it is so difficult because there are 7 key challenges to regulators. I'm not going offering the solutions. We can talk about this in the next 4 years. First thing first, just like any other changes, the hardest thing is when you have autonomous vehicle and human driving at the same time. As we go into stage 3, regulations will be much easier. But now we need to think about how do we take stage 2. It's hard to prove what is good enough. You may be asking the autonomous vehicle, okay, don't drive into a dinosaur, but there's no dinosaur on the road. And you will see a lot of people actually solving that problem. So understanding what is good enough is critical to safety because there is limited resources. It's almost the same asking yourself, like, how long should one be driving on a provisional license before they can allow to be on the road? It's the same trick. Uncertainty is built in. There's no absolute safety. Safety is relative. There's a lack of standards. We need to harmonize it. There's a public perceptions. Most of the time, the regulations are not done for substantive safety. They are done for the public perceptions. No collaborations. Now, if we think a step back, this is going to be a sector like the aviation safety, that all the airlines actually have the black box and they are actually collaborating. Unfortunately, today, each of the autonomous vehicle company are still training on their own map, on their own standards. Last but not least, how do we think about the labor issues? Yes, there is a shortage, there is a gap, but there still need to be some regulations in place. This is a little bit beyond the safety, but it's critical. That's why there are a couple of framework. AV Driving 4.0 in the US is one skeleton guideline, but I think there needs to be a call for more. My last conclusion, infrastructure and industrial innovation has to be together. Not all problems are solving an AI goal. This could be simplified problem first. In my view, having the autonomous vehicles run before the roads are actually properly built, there is a digital transformation, digital twin. It is actually a waste of a lot of social resources. You don't need the best AI if you first simplify the business problem. That's why traditionally we have this internet startup on one end and then transportation on the other end. This is a linear function, but we need to change. We need to, through policies and ecosystem as a bridge, bring it back into a circle. This is an ecosystem that the autonomous vehicle drivers and the companies need to work with the infrastructure and the industry. In the end of the day, this is not just about autonomous vehicle. I call it the AECV, or sometimes I call it the AECSD. That you need to have autonomous electric and connected vehicles working in the smart cities with the digital twin as the foundation. It's a system of systems. Therefore, building a common infrastructure like simulation platform maps are critical. If we want safety, we need to lower the bar and make sense for it. If you're trying to make the provisional license and the driving test extremely difficult, it doesn't improve safety because human has a biological limitations. This is my last slide. There are a lot of low-hanging fruits. If you go to Texas, you will see all these crazy signs. What's the point of being humorous, like saying, caution, zombies ahead? That would just cost $1 million for the perception engineers and the planning engineers in autonomous vehicles solving what does zombies ahead mean. Now, in the flip side, there's as much that the policymakers and the human can do before the autonomous vehicle work. Not all problems are autonomous vehicle problem. There are road signs problem that is simply a design problem. There needs to be collaboration and there needs to be a new mindset. Thank you very much.
Super, Paul. That was a really good overview and a hell of a lot of content in there. I saw someone asked about the slides. I believe obviously the presentation is being recorded, so I think that would be the best way for you to catch up on those. And I think that sets us up really nicely, Paul. Those a few of the things that you pulled out on your 7-point list. How to prove how good enough is. Talk about the uncertainty and certainly the standardization are all part of the talks that are coming up from our next speakers. So Our next speaker from University of South Florida is Arman. Arman, are you there?
Yes, I'm here.
Perfect. So I'll hand over to you, and then for questions, we'll wrap up right at the end. So I just want to make sure everyone has their chance to talk because it's a very diverse mix of speakers, and then we'll have the questions at the end. So over to you for your presentation.
Sure, sounds good. Okay, let me share my screen. Okay, so hi everyone. This is morning here, so I would say good morning, but I know some places it's afternoon, evening, or night. So today I'm planning to talk about testing and verification for the security and safety of connected and autonomous vehicles. So I'm Arman Sargorzai. I'm a faculty at University of South Florida. So I have a mixed background. I have both electrical and mechanical engineering background. And I was a faculty member in different universities for almost like 7-8 years during past several years. Most of my research focuses on testing and verification of connected and autonomous vehicles, also cybersecurity and security of network control system and multi-agent control system. So I'm trying to make it really short, and I just want to show you some videos and demonstrations about what we are doing today. So I'll start with my Ranks Lab team. So I have talented PhD students that they are working in our lab. I have really great, excellent undergraduate students that they are doing great work in my research lab toward testing and verification of connected and autonomous vehicles. And I think Paul already talked about how safety is important for connected and autonomous vehicles. And also, I'm going to add to that, and I'm going to talk about why cybersecurity and security is important, because these two are tied together. So as we heard, autonomous vehicle or connected and autonomous vehicles are coming, and everyone, they were excited about this fact, and they said, oh, that's a great thing. We are going to reduce number of crashes. As you know, 94% of total crashes, they are because of human errors. And then we are saying that autonomous vehicles, they are going to solve this issue, and we are going to have less number of crashes in the future because of autonomous vehicles. But we are still right now, I remember when I was listening about autonomous vehicle, they were saying 2020, now 2030, 2040, who knows exactly what day or which year they are coming fully autonomous vehicles. Still, the technology is there, but there are a lot of challenges with safety and security of those vehicles. That's one of the problems that our lab is working on. So I'm going to share with you a story. It's a life story. So I used to live in Gainesville, which is in Florida. It's north of Florida. I showed it in the map here. And I used to work at Florida Polytechnic University for almost like 4 years. So you can imagine, like 4 days a week, I was going back and forth between University of Florida to Florida Polytechnic University, which is around like 120 miles each way. So if it's interesting, yes, I was changing the oil for my car so very often. And I was going basically a week, 1,000-something miles per week. So interesting enough, during my trips from Gainesville to Lakeland, I witnessed a lot of different challenges because I was going through highway, 2-lane highway, freeways, and I witnessed a lot of different challenges, which as a human being, I was trying to solve them, or I was trying to make a decision for the first time in my life. So how we can teach those autonomous vehicles is a big challenge, because I witnessed some specific challenges which autonomous vehicles they might not face in the whole driving or the testing or the whole time of that they are working on. So one of the interesting challenges which I was thinking about during that time, it was how we can test those vehicles, how we can make sure they are safe. So on top of all of those safety issues which we have to test, we have also cybersecurity issues, because how about if hackers and attackers, they want to attack those vehicles in the future? So that's a big challenge which we are going to have. So when I started to put this in perspective, we have started to think about how to do the testing and verification of those CAVs. So we came up with several different questions: how to generate interesting edge cases. We also wanted to find out how to test about all possible cases or all possible scenarios, which is something that we might not be able to do. But is it possible for us to look at different cases and say this case is equivalent with another case? And most interestingly, how we can do that through in a mathematical manner to make sure that these cases are equivalent with each other. How we can make sure that we have some sort of coverage analysis to say this is enough for testing. But again, we cannot say exactly when is enough. So it depends really on different industries and depends on the policymakers, but we can come up with some sort of coverage analysis. So the other questions that we started to have, we witness AVs and we hear with AVs, they have crashes. Is there any specific systematic manner or systematic way that we can learn from these crashes, already happened crashes, and we can test the vehicles through these scenarios? So that's another way that we are also studying and generating scenarios. We look at the already happened crashes and we generate scenarios. The second big problem we have is environmental and sensor testing. So how the perception of CAVs performs under electromagnetic fields. How is it going to work under heavy snow or rain or even lightning or weather conditions? So those are the other challenges we have with testing and verification of connected and autonomous vehicles. The other challenge we have is, as Paul mentioned, we are going to use these CAVs in an environment that they are going to work with other conventional vehicles like human beings. So what is the language of driving? How they're going to interact with other human beings? So that's a big question we have, how we can come up with a specific language for driving that we can test the vehicle to make sure that those CAVs, they are safe and secure. The other one is how ethical those autonomous vehicles are. So this is a big challenge and everyone, they are thinking about it. How we can test how ethical are those CAVs? Those are other challenges that we are trying to look at them in our lab. And last one, which is the most important one in my opinion, because I'm working on cybersecurity aspects for several years, is cyber physical attacks, or cyber attacks. How we can test the security of CAVs, because security, as I said, it has a direct connection with safety, and also how we can check that, how we can generate false failures and attacks on different sensors, on the perception, on the actuations or actions or control algorithms, or even in the planning that Paul was mentioning before. So how we can make sure that those algorithms are safe and secure. So in order to do that, we started several years ago with software in the loop testing and verification. So as you know, software in the loop testing and verification is really great, it's really fast, and we can do and you can perform several different testing in a matter of seconds. But the problem is that it's not accurate. So in order to make it more realistic, we switched to hardware in the loop simulation and testing, so which is going to be much more accurate. But the problem with that is still it's not as accurate as real world testing. We have a problem with real world testing is the fact that imagine that we want to test a situation that a car is approaching an intersection and a pedestrian is passing by that intersection, and we want to inject some sort of cyber attack to the vehicle. So we want to see if these two, they are going to have collision or not, which is not going to be happened in real world. We cannot test this in real world. So that's why we came up with another strategy for testing that we call it mixed reality platform. This mixed reality platform is going to put the vehicle in one location and it's going to put the pedestrian in another location. And using communication, we are going to, in the simulation environment, we are going to put them in interaction with each other, and we are going to generate attacks, faults, and failures. And we are going to see how the vehicle is going to perform under those situations. We have a fleet of vehicles. Right now, we have a Ford Fusion hybrid, which we extensively modified it, and we added all different sensors, GPS, IMUs, and we developed our own autonomous algorithms. We have another vehicle, which is a Mustang Electric Mach-E. Our students also made it autonomous, and we are adding all different sensors to that. So we have those as a real world vehicle or autonomous vehicles for us. And then we have like our simulated environment, which is going to make the interaction between our autonomous vehicles and other actors. So we have two machine learning algorithms. One of them is going to generate cyber attacks, faults, and failures. And another one is going to generate edge cases. So edge cases, it can be through digital twin, it can be through our database of crash database, or it can be edge cases that we are generating based on our machine learning. And we are going to test the vehicle for their safety and security in a feedback loop. So in order to show you how it works, I have several videos, so I'm going to skip this one because the second one is almost talking about this. So this video is specifically talking about how we are doing the test in vehicle in the loop environment. I just have to run it.
In which connected and autonomous vehicles are tested in terms of security, safety, and efficiency. Since 2006, automotive-related cyber attacks have increased in prevalence by over 600% and are likely to continue as technology further pervades the automotive industry through drive-by-wire systems, sensors, and especially V2X communication technology. While the physical system of an automobile has become drastically more secure in recent years, connected vehicle technology is still new, untested, and unproven. Just as was the concern with insecure physical systems, insecure communications can result in widespread disruption and chaos when an adversary injects a malicious message or causes a delay in vital communications. The foundation of the system is a passenger vehicle that has been extensively modified and outfitted with a completely programmable drive-by-wire kit and high-precision GPS and IMU. This kit, coupled with IPG's real-time target machine and carmaker software, allows for the vehicle to be placed into a virtual testing environment while also carrying out its actions and decisions in the real world. The importance of this aspect cannot be overstated, as it allows for real-world vehicle dynamics and motion to be fed back into the simulation in real time. To demonstrate what vulnerabilities look like in the real world, we will subject our platform's automatic emergency braking system to a false data injection attack. The attack will increase our virtual radar signal data such that our vehicle appears slower and further away from the leader vehicle. This will be illustrated with 3 test runs, one under normal conditions, another with an increase of 1 meter per second, and lastly, a test with 2 meters per second. This is our control run. Notice the car's stopping position relative to the marker.
Just quickly talking about this is a simulated vehicle which we are going to test and see how our real vehicle is going to stop by this simulated vehicle.
Next up is our first attack run of plus 1 meters per second. The vehicle stops slightly later than the control run. This last test is with an increase of 2 meters per second and makes the attack effect quite apparent. As illustrated by these 3 tests, false data injection attacks impacted the algorithm's ability to safely stop our vehicle and demonstrated its vulnerability to attacks and disturbances.
Okay, so this specific video, we showed that autonomous vehicle in general, they are vulnerable to false failures and cyber attacks. In the next video, which is my last video, so I'm going to show how we develop new algorithms which are robust to false failures and attacks, cyber attacks, and then how we can test them again.
Adaptive cruise control algorithm performs against adversarial attack. In our test scenario, both the test vehicle and the simulated lead vehicle will accelerate to 3 meters per second. 15 seconds into testing, both vehicles will accelerate to 6 meters per second. 5 seconds later, the lead vehicle decelerates to 3 meters per second, and after another 5 seconds, a simulated FDI attack is injected. The FDI attack increases the leader's acceleration reference signal, leading the follower vehicle to act as if the leader vehicle is traveling faster than it actually is. In the case of a traditional controller, such as a PID, this will likely lead to a collision between the vehicles. Our observer-based controller, however, is designed to not only detect, but to also mitigate such attacks. The follower's controller uses the leader acceleration as a reference signal to determine whether the lead vehicle is accelerating or decelerating. Using this, the distance between the vehicles is derived and used as the set point for the algorithm. A neural network monitors the reference signal to detect and estimate the magnitude of faults and attacks to produce an error signal to mitigate any disturbances. The observer also monitors the signal in order to estimate the true system states to define a control signal appropriate for maintaining a safe following distance. Testing will be performed on our research vehicle by uploading a model to a micro Autobox 2 that interfaces with our test vehicle's CAN bus to receive sensor measurements and send actuator commands. Our model was developed in MATLAB Simulink and uses the DSpace RTI CAN block set to interface with our vehicle's actuators. By using a DBC file, our model is able to translate the control signal into CAN messages. In the following plots, various performance metrics are displayed for comparing our observer-based controller against the traditionally designed counterpart.
I'm going to stop here for the time issue.
When under attack,
so in this specific one, we had a cooperative adaptive cruise control. And what we did, we injected false data injection attack when the acceleration of the lead vehicle is transmitted to the follower vehicle. Our lead vehicle was the simulated vehicle, and our follower was our real world vehicle, which was the Ford Fusion. And we were able to detect the FDI attacks in real time and compensate for that in order to do not have any collision. So thank you so much. This is my information. If you guys have any questions, you can obviously ask me questions, and we can talk about it at the end of this presentation.
Excellent, Armand. Thank you very much for the presentation. It was really useful, and it's really, I think it's really important to think about the sort of negative impacts of bringing new technology to the market and the cybersecurity issues that introduces. That's obviously prevalent in normal human-driven vehicles, but becomes even more important for autonomy. I think as we then start to move into the sort of real-world aspects that you were talking about, it blends really nicely into next speaker's presentation, which is Jorit. I had the pleasure of working with Jorit on the standardization work we did with the AI for Autonomous and Assisted Driving Initiative. So, and I think you're able to give a bit of a presentation about one of the aspects that we covered in that work. So over to you.
Hi, Bryn. Hi, everybody. Yeah, my name is Jorit Kuipers from the Netherlands. And we were a part of the focus group Artificial Intelligence for Automated and Assisted Driving. And I will start up my presentation. Let's see if I can switch to the next slide. Yes. So we were asked to write a report on the implementation of safety data protocols and how we use them in practical demonstrators. I was leading the group, but I got assistance from Niels de Boer of Cetran Singapore and James Long of TRL England. And we described the implementation of safety data protocols in 3 demonstrators. The Smart Mobility Living Lab in London of TRL. Cetran had a use case in Singapore, and our own case is in the Netherlands. It's called Columbus, and I will focus on Columbus because of the little time. So in the Netherlands, we work on a project that we call Columbus. It's an acronym for Connected Level 5 Unmanned Buses. And what we try to do is to enhance the capacity of public transport, so the moving of people, by lowering the cost per kilometer per person. And we also focus on speeding up the licensing process. And the main target is to develop a free of charge open source autopilot and auto examiner, because this free of charge autopilot can reduce the cost of the public transport and increase the capacity. And we focus on three types of buses: mini buses for 1 to 2 persons, the taxi buses, but also the large buses. We have several projects in the Netherlands where we are going to drive on the road. We have 2 types of driving. We start with driving level 5 on bus depots, or level 4 because it's a restricted area, but without an operator in the vehicle. And we use shadow driving to drive with the autopilot at high speeds in public areas. So this shadow driving means that the autopilot and sensor system is in the vehicle but not connected with the vehicle. So we can make we monitor the human driver, the bus driver, and we set up a driving style of this bus driver, and also having the actions of the autopilot and compare those with each other. And this way we can drive many kilometers in the real environment and scenarios, and see and compare the performance of the bus drivers and the autopilot. In my presentation, I focus now on safety metrics that we use. That was also our goal in this technical report. And our background is in the training and assessment of human drivers. And we use the national driving procedures as our metrics, because those are the legal metrics for driving schools, and also the examiners and the drivers themselves and the police for the assessment of violations. And it's a uniform methodology for the risk mitigation. So during the examination, the examiner looks at the performance of the student and assess the mitigating actions in several situations of these human drivers. So this is really the backbone of our methodology, that we use the driving procedure as algorithms for assessing the data that we get from the performance of the autopilot, and we compare them with the data we have on human driving performance. So that's the reference model for the assessment of the performance of the automated vehicles. This safety metric is developed by one of my companies, Green Dino, and we call it the safety state framework. And what we try to do is to determine the driving style of the human driver or the autopilot, and use safety performance indicators for it. And we combine those safety performance indicators in several scores, like a driver safety score. And this driver safety score, we already validated for the use in driving simulators. So our driving simulator, for example, is used for medicine testing, because the behavior in the simulator is applicable for also the behavior on the road. So the effect of medicine on the driver safety in a simulator is applicable to the real environment situation. And here we can see an expanded report on the safety, in this case, human driver. And the interesting thing is that if we look at keeping safe speed, I don't know if you can see my mouse cursor, but here we see that there is a lower score on turning right on safe speed, meaning that the speed is too high cornering to the right. And it also directly resulted in a less score for the viewing behavior. So you get some tunnel vision if your speed is too high. So the score for viewing behavior before turning right is lower. Because of the tunnel vision, you don't look, for example, to the left, and that's a safety issue. Also, we see that human drivers forget to use the indicators if their speed is too high turning to the right. And this is also a serious safety indication. So we could accumulate all those scores into avoiding risk scores and also safety scores. And we proved that for human drivers, this relates to accident involvement on the road. So what we see in a driving simulator, using our digital twins for driving, those values are applicable to the road. So this system we are now using as a backbone for the assessment of the automated vehicles, the autopilots. I have here a video showing how this looks like. And we will start with an example of applying our safety risk metrics to our digital twin. We have here a situation where a vehicle having a bicyclist in front, it will try to take over, but it sees that the safety risk increases and it goes back to its lane. It's also viewing that there's a blocked side on the left and it will not now take over the bicyclist, and also there is a traffic light in front, so it will stay behind the bicyclist. And you see some risk graph, and that's used for determining the safety situation and also the mitigating action. Here you see an example. We use Renault Twizy's electric vehicles and automate them because they're very handy in use. And here we control the vehicle with our digital twin on a telephone in a 4G network in our office. So we synchronize the digital twin with the real environment, and all the actions are determined in our digital twin. So we have a real remote control of the vehicle, and also the autopilot uses this digital twin. Here you see that we drove with this Renault Twizy nearly 80 kilometers per hour without a driver in it, to show that it's possible to drive at high speeds. And this is a very simple ODD, so no people were involved because this was not possible at the moment with the sensor configuration on this vehicle. And at lower speeds, in the next minutes, we will see that we use a robot for the interacting with pedestrians, and we use this robot especially if we drive at very high speeds. We cannot use a human for it. There's some turning of the vehicle. So here's the part about the interaction with pedestrians. We use a robot for it. And here we try some stopping behavior using the digital twin and the safety area in front of the vehicle that enlarges with the speed. And here we have the example of the usefulness of a digital twin. This is a Renault Twizy adjusted to a multi-purpose vehicle. It's interacting with a traffic light. And behind the traffic light, I'm walking and I'm disappearing behind this truck. But in the digital twin, I'm synchronized and I don't disappear because I exist and I have a speed. So the vehicle stops because it expects me to come behind the vehicle, and it slowed down and it will go further and pick us up and drive along the route. So I think this gives a good example. We start with little vehicles at low speed at the bus depot. And when the autopilot proved to be as safe as the human bus driver, we go to a situation without a bus driver and go to the road. First we use the shadow driving on the road and are not connected to the vehicle. If the autopilot drives well in a real life situation, it can take over some parts of the route. The bus driver will be behind the steering wheel, and if that goes well, we go to remote control and the driver will be out of the vehicle. So this gives an idea of our Columbus project and how we use our own safety metrics assessment system for monitoring of the safety performance of the automated vehicle. So this was my presentation, Bryn.
Yeah, super. Thank you very much, Jorik. I really appreciate that. It's good to see the work that you're doing as always. Our next speaker is from University of Freiburg. Kshitij, if you're there.
Yeah, I'm here.
Perfect. And I think, Kshitij, on your research area looks at uncertainty, as far as I'm aware. So
Yes,
obviously, if we're creating these digital worlds, if we're creating like a digital representation, they aren't always accurate. So there's some level of uncertainty, which introduces risk into the environment, just like humans have risk, whether they perceive things correctly or not. So I'm really interested and looking forward to your talk. So over to you, please.
Oh, thank you, Brian. Let me share the screen. So it works, I guess. Perfect. Okay, hi everyone. I'm Kshitij Sirohi from University of Freiburg. Wait a second. Stop share, I think. Okay. Yeah, let's start again. I'm Kshitij Sirohi from University of Freiburg, and I'm currently pursuing my PhD under the supervision of Professor Wolfram Burgard. And my generally research area belongs to autonomous driving, and I touch various aspects such as perception, localization, and mapping. And today the topic is a step towards reliable perception for autonomous driving. And my aim is to give you a general overview what is required to make perception reliable and robust for different environments, and how we can trust it actually. And it will be a super high level. So I aim to give you some information so that in future, if you work in the field, that you have some knowledge about it. And yeah, we can discuss later about this also. Okay, let's go. So first of all, I think you guys have seen this picture somewhere where everyone is worried about AI, and my network end up detecting a cat as a dog. Why does it detect it as a dog? And for this, it's funny, but for autonomous driving, it can be really, really dangerous. And you need to have a safe system to take care of such cases. So we have seen already from Paul's presentation that autonomous driving stack looks like this. You have sensors like camera, LiDAR, radar, IMU, GPS. They extract the information of the surroundings. And after that, these information is used by the perception. What it does is it tries to find, like, let's say, human in the scene, or like drivable regions. And these are classified into different tasks. This information is then used by other downstream tasks like localization, planning, and control. So perception is one of the key component of the stack, where a proper probabilistic output is necessary. Just imagine if your perception says there's not a human on the road, it will be really drastic in case of autonomous driving. So today we will see like how we can take care of that. So here we see a diagram of supervised perception. Supervised perception is nothing but where you have a data, where you provide a label data to a neural network. Most of us know that deep learning based neural network are the way to go for perception systems in autonomous driving these days. So you provide, let's say, a lot of different cars, a lot of different person, and you expect a network to detect it as a car or a person. So after the training, you give it a input as a person, it detects a person, a car as a car. But what happens if I give it a dog? Of course, it cannot detect anything else except car or person. And the way we train networks, generally, we make sure the network is happy when it's super confident. So in this case, the network will actually end up detecting dog as a car and say, oh yeah, I'm 90% confident and dog will be a car then, but that's not what we need, right? Now let's see some example from real world. So here, the same thing, the car probably have never seen this bullock cart or cart, and now it's confused. Is it a truck? Is it a motorcycle? Is it something? And actually it also shows truck on a truck or something. So yeah, a person moving behind truck, for example here. Second example, a moon being detected as a traffic light, a yellow traffic light. Here, thankfully, there was systems in place to take care of this situation, but now just imagine it detects it as a red light and can slam brake on the highway. This is again super unsafe. Then there is another concept, as we were seeing with the radar presentation. So you can inject some noise, and then the network can become overconfident. So you see a picture of panda, network was 57% confident that it's panda, but after noise, it says 99.3, it's a gibbon, which is again a safety issue. And last but not the least, unseen environments. So you can end up training your network at a really nice place, and then you encounter something like this. Network has never seen these traffic agents or like rickshaws and like such a crowded place, which is also not important, which is also super important. So the key idea is to, of course, you have to make network learn some classes or some objects like car, person. You cannot have all the classes in your data, but also give it a sense of, I don't know. So if it's encounter something new, yeah, it detects something like, let's say 50% car, 50% person, which means the network is saying, I don't know. So that's our aim. And that can be achieved by actually having an uncertainty aware perception, where you have like not just the classes, but also you predict uncertainty, which actually tells you how confident you are in any result. And there are various methods, we'll not go deep into it. But having a dedicated system to detect uncertainty is super crucial for this safe operation. Before we go into my research, let's check some segmentation. So there are three kinds of segmentation. Segmentation is nothing but a task of extracting information from the surrounding. So if you are given input image, then first task is semantic segmentation. Now you can see wherever there is a blue, this means it's a car. So semantic segmentation aims at predicting a class or object for every single pixel. So it can tell this pixel belong to a car, this pixel belong to a human. So human is in red and car is in blue. So as we can see here, and similarly like road is in violet. Then one thing you can see here is even though they are different cars, they are all detected as one because semantic segmentation only detects a object. Now, then the second segmentation task comes is instance segmentation. What happens there is you not only detect a class of a object, but also separate them. So you can see all the cars are actually with different color. So you are not just detecting them, it's a car, but also detecting them separate. This is helpful for planning. So if there are two humans going in different direction, you can plan to avoid them and also other tasks. But you also see here in instance segmentation, there is no background. So we lose all the information about road, vegetation, which is useful for like driving, and these are gone. That's why recently a task called panoptic segmentation has been proposed. And here you have both the information. So you predict the instances or like separate numbers for all these objects, which can be counted, such as here again, cars and human. But also you predict the background classes such as like road or sidewalk or vegetation and so on. Yeah. So now we come to uncertainty of panoptic segmentation. We are actually the first one who actually introduced this task. So we don't only care about how well our segmentation is performing, but we also care about how good our uncertainty estimation is. But let's see what does uncertainty estimation means here. So here in semantic segmentation, you can see a corresponding uncertainty map, where the brighter things represent high uncertainty. So these regions network do not know what it is, But you see, because all the cars are detected as one, there is no uncertainty between cars. So it is confident that this whole row is car, but it is not good because different car can have different detections, right? Similarly, in instance uncertainties, now we have the boundaries of uncertainty, like network is a bit confused at the boundary because its image and both pixels are so close. So now you have like this uncertainties of instances, but again, the background is missing. So we proposed the task of panoptic segmentation with uncertainty estimation, where you have both uncertainties of instances and the background classes. This helps you to have an overall picture and overall uncertainty estimation about your prediction. We also propose metrics to evaluate it. So it's not just predicting something that we don't know. It can also evaluate if your uncertainty estimation makes sense. Okay, so how can we actually visualize if our uncertainties have any information in it? So let's check the example B here. So we have a suitcase. Network was never trained to predict a suitcase. And then in the error map, we see it is actually making an error. So every red region is defined that where network actually makes up the error. And you can see it's getting high uncertainty. So it can be predicted as a road. It can be predicted as anything because network does not know what suitcase is, but it's giving it high uncertainty for us to make a decision. Okay, let's not take these regions into account and only take the places where we are more certain, like humans or like roads. And this helps us to make informed decision. And now we will see a video. So you can see on the left, the panoptic segmentation, all the instances or all the different objects are defined by the white boundary. And you can see on the right, the panoptic uncertainty. So you can see network is making high uncertainty or is more uncertain where there is shadow or the things look similar like sidewalk and road when they merges together. So actually network is able to predict well uncertainties well here. So we can see that. Okay. Now for a really good question here would be what happens when we just train it in like Europe and test it in India. So here are the results. The network never saw these images during the training. And you can see now in India, there are a lot of things. First is the tuk-tuk in the last image. And it never saw a tuk-tuk or auto rickshaw in Europe. So it predicts, of course, something like a car or something because it's the nearest. And then you can see high uncertainty exactly in the shape of this auto rickshaw. And of course, it's also making error because it never saw something like that. Similarly, in the first image, there's no proper lane markings. And network here is predicting that everywhere you can drive, which is wrong. As a human, we can see we can't drive here or we should not drive here. But in uncertainties, we can see a clean road map. So network knows, okay, let's stay within the certain regions, and that's where I should drive on. So this experiment also shows that you can train on Europe and test on some other out of distribution data. We also did research in LiDAR, same concept, different approach though, but that will not go into it. So here, every point is getting a panoptic label, so panoptic segmentation of LiDAR point cloud. And on the right, you can see the uncertainties. So wherever the LiDAR point cloud is sparse, like these regions, you will see high uncertainties in brighter regions. And that's obvious because there's no shape of the point cloud and network is just confused like what to make out of it. And also at the boundaries of sidewalks and the roads, it's also making those kind of errors. So in conclusion, actually, it's fine to make errors, but it's also required if you make error to tell that, yes, I am not sure. And then I think we are getting one step towards the safe operation. So yeah, here, maybe a dog would be a better answer. And if you want to check our research, you can check on these QR codes. Thank you.
Excellent, Shitish. That's a really good explanation of a very difficult topic. So I appreciate your effort with that. It was really useful and really interesting to see the impact of training in a European environment and then moving to an Asian road environment. I think you said it was India. So yeah, no, I think it's really really interesting. I think just one question for all of the panelists, really, if you all want to turn your cameras back on now. So we've seen quite a diverse mix of information presented. In terms of AI for road safety, which is one of the initiatives that has been started within the ITU, where do you think the main focus should be? Because obviously it's a very diverse, complex, deep topic. You may have some biases given your research, given the things that you've been working on, but I'd just like to hear from each of you where you think AI can help really improve road safety as we move forward. Maybe start with Jorrit.
Yeah, I think what we do is that we model human driving profiles. And because automated vehicles will drive in an area with human drivers, it's very important to understand the human driver, also the behavior, because otherwise you have a problem. If you develop, for example, a very safe vehicle, automated vehicle, the humans will not understand it, and it will also cause us dangerous situations. So I think that AI at this point also helps to understand the human driving behavior, because I think that the developers of the vehicles don't understand human behavior as well as needed. So that's my contribution to this question.
Yeah, excellent. And maybe over to Paul.
Yeah, I think a couple of things. First, focus on the substantive safety issues. So what I mean by that is don't create a list that we think nominally is what safety means, and then try to defeat that list with a laundry list. That's one. Secondly, I think there needs to be, again, substantive framework that is practical. There are no dinosaurs on the road. There are no kangaroos in the road. So requesting how do we avoid hitting a kangaroo in US is not a safety issue. So when I'm saying that, I really mean it, because in a lot of the frameworks, because we don't know, we try to overshoot, and that overshooting is making everything more dangerous. It's with a good intention. So I would like to end it with the analogy, like this is like a newborn baby. If we're taking a lot of the past experience, it's almost like I'm a newborn parent. You have to learn it from the first principle. Just reimagine how we first take road safety 100 years ago when we start seeing moving vehicles on the road. That should be the mindset of us. Learning from the past would only help us to a certain extent, and overlearning or overfitting from the past experience is going to be the most dangerous thing that we are doing right now.
Yeah, I think that's really interesting when you look at Shetish's work, really, when you think that mobility is changing. So there's new mobility classes appearing all the time, especially with micro mobility. So when you have those things introduced into an environment that weren't there previously, if you've trained without them there, then that introduces a conflict now between what the autonomous vehicles can do and actually what the city wants to enable in terms of a more active mobility or micro mobility. So there's going to be some really interesting challenges there. So thanks for raising that, Paul. Maybe move to Arman, your views.
Yeah, so just to make joke with Paul, so I think our AI might see dinosaur on the road one day, so by mistake. So that is possible. But in my point of view, of course, like I was working on developing AI for several years for autonomous features, autonomous vehicles. But then 4 years ago, I started to change my mindset and also my students' mindset from developing to testing and verification. That's a really different world. So if all of our developers, they can change their mindset in a way that they think about testing and verification, what is going to cause unsafe situations, or what is going to, I mean, how their algorithms is going to be insecure when they are developing it, that is going to make it really much better. So in my point of view, I would say testing and verification for safety and also security of anything related to AI is really important, because we're looking for something to enhance the quality of life for people. And AI obviously it can do that, but we have to all the time make sure those systems, those features, those automated features, autonomous systems, they are safe, they are secure, and they're reliable, that they can be used in the future.
Super. And then I think closing remarks to Kshitij. So on your side, AI for road safety, what does that mean for you? And where do you see things going?
So until now, the way I see the way the research heads is, you always try to get the best performance on certain metrics, and those metrics do not have any safety protocol in it. So it's just always like getting the best performance for your segmentation detection or whatever. And that's why research also is not motivated enough to go in that direction, because it's hard to like verify those things. The established metrics and anything regarding that is not available. And I think we need to induce some kind of safety-based research, which can actually help to achieve this safe AI. Without it, research will just keep pushing towards getting better segmentation, for example. Yeah.
And so that's really the impact of how would better segmentation improve the safe driving behavior of the vehicle, not just segmentation on its own. Is that what you?
And that's exactly what people are right now most focused, because it's the easy way to do it, but hard is to ensure safety, and there's no notion of safety in our metrics, let's say like that.
Excellent. Well, I'd like to thank all of our panelists today and all of the participants around the world. It's been a really interesting session, so I appreciate everybody's contributions. Stefano, I'll hand back over to you, I believe, for the closing remarks from the ITU. So thank you very much.
Yes, thank you very much, Bryn, and thanks also to all the panelists for the interest session from our side. To wrapping up, I'd like to invite Dr. Bilal Jamoussi, the chief of the ITU Study Group Department, to deliver the closing remarks. Over to you, Bilal.
Distinguished colleagues, panelists, and dear participants, thank you for joining us for episode 26. Today, we addressed smart mobility, paving the way for road safety. The concept of autonomous driving holds the potential to reshape the future of mobility with limited human intervention. The vision is for a safer and more efficient transport system, which will be achieved by reducing human errors and enhancing responsiveness on the road, therefore preventing disasters caused by human distraction, fatigue, and reckless driving. Autonomous vehicles will communicate with each other, share information, perceive their environment, and help support coordinated traffic movements, thereby reducing road congestion and enhancing overall road safety. However, it is essential to enable testing and validation processes to ensure the safety of autonomous vehicles. For this, collaboration among automobile manufacturers, policymakers, and researchers is pertinent. Additionally, there should be comprehensive regulations and standards that govern the development, testing, and deployment of autonomous vehicles on the roads to achieve accountability. To address some of these studies, the ITU focus group on AI for autonomous and assisted driving that was established in October 2019 studied these. This focus group completed its deliverables by envisaging an automated driving safety data protocol that enables the performance assessment of AI systems on the road. The 3 technical reports from the focus group covered a protocol specification, various practical demonstrators, and ethical legal considerations. To further embrace and understand how AI can be deployed on the road with a firm commitment to safety, and to envision a future where autonomous driving and safety can coexist, the AI for Road Safety Initiative was established and launched in October 21 by ITU, together with the UN Envoy for Road Safety and the UN Envoy for Technology. It was enlightening to see the various efforts made in the field of autonomous driving and road safety across various regions, including Europe, America, and Asia, through today's presentations. I hope to see these efforts and relevant outcome be channeled into the activities of the AI for Road Safety Initiative in future. I would like to once again thank you all for attending today's webinar, and I would like to invite you to contribute to the activities of the AI for Road Safety Initiative. Please also stay tuned with us for more episodes of the Digital Transformation webinar series. The next episode 27 on digital transformation of testing federated test beds as a service is scheduled to take place on the 21st of June from 1400 hours to 1530 or 2 p.m. to 3:30 p.m. Geneva time. My colleagues will provide the link on the chat. Thank you all for your kind attention.
Yes, thank you very much, Dr. Jamoussi, for your remarks. And for everyone, this discussion does not end here. As Bilal said, we will continue the discussion through the AI for Road Safety Initiative. And also we encourage you to check out the Digital Transformation webinar series, as more episodes of this series are scheduled already, and we invite you to stay tuned. So please check the relevant links that have been put on the chat. And thanks once again to our moderator, to the panelists, to our participants. This is Stefano Polidori from the ITU. Hope to see you again at other ITU events. Thank you.